Hello and welcome to section 8.5, partial fractions. This is the last integration technique that we will be learning. We have more to do in chapter 8, but they're not going to be new integration techniques. They're going to be different things. The next section is looking at different ways to evaluate integrals besides actually integrating them, so how can you approximate them. And then the one after that looks at infinite integrals. And it's a nice segue into sequences in series, which is why we put it at the end of this section. But we're doing partial fractions, which is my favorite new integration technique from this section. Not from this chapter. Obviously, it's my favorite in this section because it's the only thing in this section, but favorite from this chapter. So, some motivation. Consider the integral dx over x squared plus x. So if you were to try to integrate this, you would first try U-Substitution. You can't do this with a U-Substitution. You then might try integration by parts, and we can't do integration by parts. Looking at this, if you let u equal x squared plus x, which is what you'd probably want to try, you would get du equals 2x plus 1, and then you have no way of getting rid of that x, so you have too many variables. You can't do a trig substitution because trig substitutions require variable squared plus or minus constant squared. And here we don't have a constant. Here we have another variable. So we can't use trig substitutions. There's no trig expressions in here, so we can't do a trig integral techniques. And there's nothing, you're not multiplying two things, so no integration by parts. So we have to do something different. And first thing I do when I see this, I just immediately think this, and you probably do too. You just immediately recognize that 1 over x squared plus x is 1 over x minus 1 over x plus 1. Just immediate. That's just like the first thing you think of, right? And the key thing here, though, is we can integrate both of these. So if you wanted to combine these, you'd get common denominator. So you'd get x times x plus 1, which is x squared plus x. So you multiply this one by x plus 1 over x plus 1. Multiply this one by x over x. You then have x plus 1 minus x, which will just give you the 1 in the numerator. So this idea of writing a fraction as the sum or difference of multiple other fractions is known as partial fraction decomposition. Okay, highlighting, and now I talk. So partial fraction decomposition is this technique. Of writing a fraction as a sum of two or more. Can't spell very well. And I'll say sum of two or more simpler fractions. You want to make it easier. You don't want to make it harder for yourself. So there are a bunch of techniques for partial fraction decomposition. Okay, there's two techniques. There's a bunch of nuances. And we're going to see all of those nuances, as always, through examples. So example number 1 is let's just get our hands dirty doing a partial fraction decomposition. So use partial fractions to decompose 1 over x squared minus x minus 6. So in order to use partial fraction decomposition, the denominator has to factor in some way. So we try to factor the denominator. x squared minus x minus 6. Factoring that is x minus 3, x plus 2. It factors. Good job. We can actually use partial fractions then. So the goal is to write 1 over x squared minus x minus 6 as something over each of the factors that you get when you, factor. Each of the factors of x squared minus x plus 6. So we're going to add these two. If we end up needing to subtract them, then whatever we get for the numerators will just be negative. And then if we are looking for what the numerators are, we're just going to assign variables to them. So we'll say a and b. Okay, if we wanted to solve this for a and b, well, first thing we would want to do is clear the denominators. Clear denominators. What would we need to multiply by? We would need to multiply by x minus 3, x plus 2, which, by the way, is just x squared minus x minus 6 because we just factored it. So when we clear denominators, the left-hand side just becomes the numerator, and that should always be the case. That should always be the case. The right-hand side becomes a, and then we have x minus 3 divided by x minus 3, so we won't have that x minus 3 term, but we will have the x plus 2. And the same thing goes for the b term. The x plus 2 will cancel with x plus 2, but we'll still have the x minus 3. All right, so we now need to solve for a and b, but we only have one equation. There are two main methods for doing this, of doing this. I'll show you both. I do have a preference of what I like to do, but it's mainly just because that's the one I like. It has no, I don't think it's easy or anything. It's just the one that I prefer. So you can make your choice which one you like the best. And let's try to do this on half a screen. So way number 1, let me rewrite this up here so I can scroll some. Okay, so way number 1 is this equation. This equation must be true for all x. So we're going to pick certain x and evaluate it at those x. And we normally pick the x's very strategically. So we evaluate it at nice values of x. And this is the method I like to use. So first, let's evaluate it at x equals negative 2. So we are choosing x equals negative 2 because when you plug it into this expression, we're not going to have an a term. We're going to get rid of one of the variables. So we have 1 equals a times 0 plus b times negative 5. So that means that b is going to equal negative 1/5. Let's divide by negative 5. All right, that got one of our variables, one of our coefficient variables. We have a lot of variables floating. One of our letters. How about that? So now we want the other one. We chose x equals negative 2 to cancel this term out. So now we'll pick a value for x to cancel this term out. So we'd say when x equals 3, we have 1 equals a times 5 plus b times 0. So we get a equals 1/5. Okay, that was way number 1. I will now do way number 2. Way number 2 says that the coefficients, I don't feel like I spelled, I think there's an I there, efficients. The coefficients of various powers of x must be equal. All right, so we rearrange our equation that we're trying to solve. So we have 1 equals a times, I don't want to say it that way. Let's distribute the a. So ax plus 2a plus bx minus 3, which is x times a plus b, and then plus 2a minus 3b. So looking at the coefficient of x, the left-hand side does not have a coefficient of x, so we assume that's 0. So we have 0 has to equal the coefficient of x on the right-hand side, which is a plus b. So a has to equal negative b. Then, looking at the constant term, we have 1 equals 2a minus 3b. But we said that a was negative b, so we have negative 5b. So b has to equal negative 1/5. And then plugging that into a equals negative b, you get a has to equal positive 1/5. So those are the two ways of solving for a and b when doing a partial fraction decomposition. Then to finish the problem, we have 1 over x squared minus x minus 6 equals a, which was 1/5, divided by x minus 3, plus b, which was negative 1/5, divided by x plus 2. And that is how we would decompose 1 over x squared minus x minus 6. So if we were integrating this, then we'd break the integral over the sum, and then we integrate both terms, and this will just be 1/5, pull that constant out, and the integral of this will just be a natural log. Okay, so now that we've seen an example of partial fractions in action, let's do an example where we actually integrate something. Go back to some calculus. All right, so evaluate the integral of x plus 15 divided by 3x minus 4 times x plus 1 dx. So why don't you pause the video and try doing the partial fraction decomposition for this expression. And if you're feeling up to it, go ahead and integrate the result. And then unpause to see if you did it correctly. Okay, so solution, we use partial fractions. So we say x plus 15 divided by 3x minus 4 times x plus 1 equals a over 3x minus 4 plus b over x plus 1. Clear the denominator. You get x plus 15 equals a times x plus 1 plus b times 3x minus 4. And then you pick strategic values for, I'm doing way 1, so you'd pick strategic values. So when x equals negative 1, trying to get rid of a, we have 14 equals b times negative 7. So b equals negative 2. So looking at the next one, we could choose 4/3 to get rid of b, But then we'd have fractions. I don't really want to deal with fractions. So let's use the fact we've already found b and just pick an easy value. Just pick x equals 0. So when x equals 0, we have 15 equals a minus 4b. Well, a minus 4b is a plus 8, since b is negative 2. So then a would have to equal 7. Okay, so our integral is now, break this, we have the integral of quantity a over 3x minus 4, so 7 over 3x minus 4, plus b, which was negative 2 over x plus 1 dx, which is 7 times the integral of dx over 3x minus 4, minus 2 integral of dx over x plus 1. Make some substitutions. Let u equal 3x minus 4, so du equals 3 dx. And for the other integral, let u equal x plus 1, so du equals dx. Stop it. So this would be 7/3, the 3 coming from our du equals 3 dx. Natural log absolute value of 3x minus 4, minus 2 natural log absolute value of x plus 1, plus c. I skipped a step there. If you were to, I skipped the substitution. I wrote down what the substitution was. So I guess I didn't really skip a step beyond that. But we will be doing enough of these integrals with the partial fractions. You should get comfortable enough to just go from here to here. Maybe writing this out if you need to. But I plan on just skipping straight from here to here. Okay, next example. So I said there was a lot of nuances to this partial fraction decomposition, so we're going to start seeing those. So nuance number 1, let's evaluate the integral of 5x minus 2 over x plus 3 squared dx. All right, so nuance number 1, notice we have the same term. So this is x plus 3 times x plus 3. That is what the squared means. But because it's the same term, we have to do something different with our partial fraction. So since we have a repeated factor, in the denominator, we have partial fraction decomposition would be 5x minus 2 over x plus 3 quantity squared. We have a divided by x plus 3. And then we have b divided by x plus 3. This would be wrong, because notice you could just combine the two, and then you'd only have 1 power of x in the denominator, not 2. So what we do is we square the bottom. So if we had a x plus 3 quantity cubed, you would have a over x plus 3, b over x plus 3 squared, then you'd have plus c over x plus 3 quantity cubed. You just keep adding a power of whatever is being raised to a power in the denominator. Okay, solve this partial fractions. So you'd clear denominators. You get 5x minus 2 equals a times x plus 3. And what's very nice is you just get plus b. Okay, when x equals negative 3, the left-hand side is negative 17, and the right-hand side is just b. So you just immediately get b right there. You then need to pick another value to try to figure out what a is, I'd prefer a having, I'm going to just do this. When x equals -2. You can pick any value here. I just chose x equals -2. That would be -12 equals a. I chose it so I would just get 1 power of a, or 1 of a. And then plus b, which is -17. So a equals 5. So we have the integral of 5x minus 2 over x plus 3 quantity squared is 5 times the integral of 1 over x plus 3 minus 17 integral of 1 over x plus 3 squared. Notice I just threw a bunch of steps together. I just basically just use the linearity of the integral and pulled out the constants. See the previous example if you would like more details. First one is just 5 natural log absolute value of x plus 3. The second one, you would let u equal x plus 3, so du would equal dx. And then you'd have the integral of u to the -2nd du. Integrating that, you get a negative sign popping out of it, so plus 17. And then you'd have u to the -1st, which is just 17 over x plus 3. Okay, next nuance. We're going to evaluate the integral of, this one's a long one, -2x plus 4 divided by x squared plus 1 times x minus 1 squared dx. So, first off, the nuance that we are looking at is here we have a non-linear term that is irreducible. We cannot factor x squared plus 1, but it's not linear. It's not just x plus 1, it's x squared plus 1. So how are we going to deal with that? That's the nuance that we're looking at. Also, we just have a lot of things going on here. This example is just meant to show you that the partial fraction decomposition can get quite complicated. We use partial fractions. So we have -2x plus 4 divided by x squared plus 1 times x minus 1 squared. So I'm going to write down something wrong first. So you get a divided by x squared plus 1 plus b divided by x minus 1. And then we saw, to deal with the fact that we have a factor squared, we do c divided by x minus 1 squared. So to deal with the irreducible non-degree 1 term, we do ax plus b. You're going to take every possible power of x that is less than the degree of the irreducible term. So if this was x cubed plus 1, first off, that would factor, but let's ignore that. You would do ax squared plus bx plus c, and so on. Okay, solve this. We clear denominators. You get -2x plus 4 equals ax plus b times x minus 1 squared plus b times x minus 1 x squared plus 1 plus c times x squared plus 1. We have 4 variables. Oh, I'm sorry. I have two variables defined the same way. So let's do ax plus b, c over x minus 1, and d over x minus 1 squared. Shame on me. Okay, we have 4 letters we're trying to solve for, so we're going to need 4 values of x. Okay, so when x equals 1, that's going to be the easiest one, we get 2 equals, this, we still have an x minus 1 term, so this all goes to 0. We still have an x minus 1 term here, so the c term goes to 0. So we just get d times 2. So d has to equal 1. So that's nice. Letting x equal 1, we just got d. Next, notice that we've already used x equals 1, so we can't clear these anymore. And no real value for x will clear x squared plus 1, since it's irreducible. So now you just pick 3 values for x that you think will be easy. So I'm going to let x equal 0, because I think that'll be easy. Then you'd have 4. X equals 0 is also nice because it kills the a. Then we'd have b times negative 1 squared, which is 1. Minus c, because we'd have negative 1 times plus 1. And then plus d, but we said d was 1, so plus 1. Okay, so that is b minus c equals 3. We're going to call that equation number 1. Pick another value that we think will be nice. I think 2 will be nice, because when you plug in 2, x minus 1 will still be 1. When x equals 2, you have 0 on the left-hand side, equals, as we said, this term will be 1. So you just have 2a plus b, plus this term will be 1, this will be 5, so we get 5c. And then plus 5d, d was 1, so plus 5. So we have 2a plus b plus 5c equals negative 5, which we will call equation 2. We've ran out of nice values, so we just pick a small value for x. So I'll pick negative 1. When x is negative 1, you get 6 equals negative a plus b times negative 2 quantity squared is 4, plus c times negative 2 times 2, and then plus d, which is just 1, times 2. Well, swing the 2 over to the other side, and you get 4 equals, it looks like 4b minus 4a, and then also minus 4c. Divide everything by 4, and you get 1 equals b minus a minus c, which we will call 3. Okay, now we have 3 equations, 3 unknowns, we need to solve them. So, looking at this, we have b minus c, and we have b minus c showing up in 3. So let's combining 1 and 3. We get, well, 1 equals b minus c minus a, rearranging equation 3. But we said b minus c is equation 1 is 3, so that is 3 minus a. So 1 equals 3 minus a, so a equals 2. Okay, that's nice. We have a equals 2, so now we need to somehow get rid of b or c. Well, we have 1b and 1b in 2 and 3. So if we subtract the 2, then we'll get rid of b altogether. So doing 2 minus 3 we would get, looking at -5 minus 1 is -6. Uh, 2a minus -a is 3a. B minus b is 0. And 5c minus c is 6c. So we get 3a minus 6c, plus 3a plus 6c. I said it correct the first time. Okay, but we said a was 2. So this is -6 equals 6 plus 6c. Solve this, subtract 6, divide by 6. We see that c is -2. Plug this into equation 1. You get 3 equals b minus c, so that's plus 2. So b equals 1. Cool. We found all the letters. So now let's go back and answer the problem. So we have the integral of -2x plus 4 divided by x squared plus 1 times x minus 1 squared dx. This is using the linearity of the integral. This is the integral of ax plus b. A was 2, so that's 2x. B was 1 plus 1 divided by x squared plus 1 dx. Plus c. C was -2. Integral of 1 over x minus 1. Plus d. D was 1. Integral of 1 over x minus 1 quantity squared. Okay, break the first integral up even more. We get 2 times the integral of x over x squared plus 1 plus the integral of 1 over x squared plus 1 minus, go ahead and integrate the last two. That's minus 2 natural log absolute value of x minus 1 minus 1 over x minus 1, and we'll go and throw in a plus c. The first integral we can do by a U-Substitution. Let u equal x squared plus 1. Then du would be 2x dx. So the first integral is just the integral of du over u. So that's the natural log absolute value of u, which is x squared plus 1. Second integral is just a well-known integral that is tangent inverse of x. And then bring the other two down. And there you have it. Sadly enough, this is not as complicated as they get. We'll see how we could make it even more complicated with the next example. So before I give you the last example, I've shown you all of the nuances for partial fraction decomposition. Let me just summarize them real quick. So partial fractions. A. If x minus r to the m is a factor of the denominator, then we have the way we would decompose this is 1 over x minus r to the m equals a1 divided by x minus r plus a2 divided by x minus r squared plus plus am of x minus r to the m. And b, if h of x is an irreducible factor of the denominator, of degree m, So you can think h of x equals x squared plus 1 from the previous example. Then we would use on our partial fraction side, we would use a sub m minus 1, x to the m minus 1, plus a sub m minus 2, x to the m minus 2, plus dot dot dot, plus a1x plus a0 divided by h of x. And this is exactly what we did. This is saying take all powers of x that are less than the degree of h of x. So here you have h of x has degree 2, so you would just take a1x plus a0. Okay, last example. Note that in order to use partial fractions, this requires that the numerator has lower degree than the denominator. If this is not true, we have to use long division. Use long division first. So a quick little example of this. Evaluate the integral of x squared divided by x cubed in the numerator, x cubed divided by x squared plus x dx. So we have degree 3 in the numerator, but degree 2 in the denominator. So we must use long division first. So x squared plus x is going into x cubed. X squared goes into x cubed x times. So that would be x cubed plus x squared being left over. Subtract that off. You're left with negative x squared. X squared goes into negative x squared negative 1 times. So that's negative x squared minus x. Subtract that, and you're left with an x. So our integral is x minus 1 coming from our long division plus x divided by x squared plus x, which is coming from the remainder x dx. Well, that's x squared over 2 minus x plus the integral of x divided by x squared plus x. And that's x squared over 2 minus x integral. We can factor an x from the denominator and cancel it with the numerator to just get dx over x plus 1, which is x squared over 2 minus x plus the natural log absolute value of x plus 1. So don't forget this small nuance. It's very easy to forget this and then mess up on a test quiz or just in real life. And that finishes partial fraction decomposition. You will definitely be seeing this again in differential equations, Math 242, if you move on to there.